All right, so in our last explainer, we looked at what git-stage-batch can do for your day-to-day workflow. It's powerful stuff. But the real magic, the part that makes it feel so solid, is how it works. Today, we're popping the hood and taking a deep dive into the seriously elegant architecture that powers this whole thing. We're going to tackle the one question that probably pops into your head when you see this in action. How on earth does it keep track of specific lines so perfectly, even when you're busy editing and changing that same file? It feels like magic, but it's actually just some brilliant design decisions. And we're going to peel back the layers on this in 4 parts. First, we'll get into the 3 commit model. That's the rock-solid foundation. Then, we'll explore a totally different way of thinking, constraints over operations. After that, we'll see how it finds your changes with conservative structural alignment. And finally, we'll see the awesome payoff with a command called sift. Okay, so first things first, everything, and I mean everything, starts with a foundation, the 3 commit model. Every single named batch you create lives inside this framework. If you get this, you'll get how the whole system works. So what is it? Well, the model uses 3 different Git commits to create a super stable frame of reference for all your changes. Just think of them as 3 pillars that create this fixed, reliable space for you to work, even when your files are a total mess. The first pillar is the baseline commit. It's basically the before picture. It's a snapshot taken right from head, your last committed state. This becomes the historical anchor that everything else gets measured against. Pillar number 2 is the batch source commit. And this one is absolutely critical. This is a snapshot of your working tree at the very moment you save something to a batch. It literally freezes your uncommitted work in time, creating this perfect, stable coordinate system where line numbers are fixed and reliable. And that brings us to the 3rd pillar, the realized batch commit. This isn't just a patch file. Nope. It's a full-on Git commit that shows what the file would look like if you applied only the changes from your batch to that original baseline. It's the pure logical result. Now, having this 3 commit model isn't just a neat way to store data. It actually lets us make a huge mental shift in how we think about changes. It allows us to move away from the old, fragile world of traditional diffs and patches. See, a traditional patch is like a recipe, right? It's a list of steps to follow. And if you follow that recipe twice, you're going to get duplicate changes, a real mess. But git-stage-batch works with declarative rules or constraints. It's more like saying, the final result must have this line. You can apply that rule 100 times and the outcome is always the same, and it's always right. That's the game changer. And this whole philosophy is just perfectly captured in this quote from the architecture docs. In this system, there's no such thing as a replace operation. What looks like a simple replacement is actually built from 2 even simpler, more fundamental ideas. And what are those ideas? Well, every single change, no matter how complicated, boils down to just 2 types of rules. First, a presence constraint, which just says, this line has to be in the final version. And second, an absence constraint, which says, this specific chunk of code is not allowed right here. That's it. Everything is built from those 2 simple primitives. Okay, so we've got our rules, our constraints, that's great, but hang on. How does the tool know where to apply them? You've been editing the file. The line numbers are totally different now. This is where alignment becomes super important. Right, this is the core challenge. You defined a rule based on that frozen-in-time batch source snapshot, but now you have to apply it to your current, messy, totally different working tree. How does it find the right spot without messing things up? Well, the secret is something called conservative alignment. Instead of using a generic diff algorithm that might get confused and make a bad guess, it looks for something it can totally trust: unique lines. Lines that only show up once in both the old version and the new version of the file. These lines become foolproof anchors, and the system can then safely map all the changes between them. And that leads to this incredibly important design principle: prefer unmapped over incorrect. What this means is, if the system is ever even slightly unsure about where a change should go, it just won't guess. It would rather leave a section of the code unmapped than risk applying a change in the wrong place. It is always, always about correctness over completeness. So we've gone through all this careful architecture, the 3 commits, the constraints, the safe alignment. What's the big payoff? Well, we see it in some incredibly smart features, and the best example of this is this sift command. Let's picture a scenario we've all been in. You have a named batch for, say, feature X, But as you're working, you end up committing one little part of that feature directly to your branch. Now your batch is all cluttered up. It's got a mix of stuff that's already done and stuff that still needs to be applied. It's a mess. This is exactly the problem that Sift was built to solve. It intelligently looks at your named batch and compares it to your current codebase. The result? A brand new, totally clean batch that contains only the work that still actually needs to be done. And here's the really brilliant part. It doesn't just filter the old list of changes. No, it's way smarter than that. It calculates the final target state that the original batch wanted to achieve. Then it looks at the current state of your code. And from there, it figures out a completely new and minimal set of constraints needed to get from where you are to where you want to go. So you see, it all ties back together to those three foundational ideas we talked about. The system thinks in constraints, not step-by-step operations. It understands the actual structure of your file, not just fuzzy diff hunks. And it will always, always choose to be correct over making a risky guess. And when you step back and look at the big picture, you realize this isn't just a clever trick for managing Git changes. This whole model of declarative rules and conservative alignment is a real shift away from fragile step-by-step recipes. And it kind of makes you wonder, what other tools in our toolbox are still using recipes when they really should be using rules?